Greetings everybody and welcome back to another ring theory video. So before we take a look at the quotient rings, I want to quickly mention principal ideals, which are a special type of ideal, and I'm also going to give a proof of useful equality of sets that involve these principal ideals. So let's start off with a proposition / definition. What exactly is a principal ideal? Essentially, a principal ideal is an ideal that's generated by one element in your ring. So if we have a ring R, and you choose some element A in your ring, then the principal ideal of A is defined to be, well, you write it as these angled brackets with A in there. Sometimes people write this as A times R as well, and this guy is defined to be the set of all elements A times R, where R is an element in your ring. So basically over here, these are all multiples of A. This guy is an ideal, and we'll prove that. But because it's only generated by one element, we also call this a principal ideal. Okay, so let's prove that this is an ideal. It's fairly straightforward that this is an ideal by construction, really. But let's just take two elements of this set here. Let's call them S and T. Then because S and T lie inside of this set, then S is equal to A times B, and T is equal to A times C for some B and C in the ring R. Okay, and what we wanted to show is that S plus T also lies inside of this ideal, so that's the first condition for being an ideal. So let's take a look at S plus T, but this is equal to A times B plus A times C. Okay, but we can factor out an A, so we're left with A, B plus C. B and C were ring elements, so the sum is also some ring elements, so therefore this lies inside the principal ideal generated by A. And second of all, if we just have some random ring element R in your ring, then we want to show that we already have an element S in that ideal there. We want to show that R times S is inside of A. How can we show that? Well, R times S, that's equal to R times S was A times B. Okay, we can rearrange things a little bit here to make it more obvious. So this is A times RB, but R and B, these were just some ring elements. So obviously this whole entire thing lies inside the principal ideal generated by A. So these guys are our principal ideals. Let's give a few examples of this. If you take a look at the ring Z, we have these following ideals, which I gave examples of. So 2Z, 3Z, and in general, NZ are principal ideals. Because 2Z, you can generate this whole entire ideal here by one element, namely 2. And then 3, you can generate it by the element 3, and NZ, that's really generated by N. So you could use these angled brackets notation as well, but usually when you talk about these ideals here with the integers, for some reason people like to use 2Z, 3Z instead of these angled brackets here. I guess this notation is a lot clearer because clearly this guy is an ideal in your ring Z, whereas this notation here, you're kind of assuming that, well, your original ring was Z. It's not too clear. And here's a fact over here, which we'll get to after quotient rings. It turns out that all ideals of Z are principal. And this makes the ring of integers a so-called principal ideal domain. So a principal ideal domain is a ring where all of its ideals are principal ideals. And we'll get to PIDs in one of the later videos after quotient rings, because we're going to prove a few nice properties about these sorts of rings. Let's take a look at another example. We're going to let R be the complex numbers, but then we adjoin, let's say, two variables x and y. The fact that this is complex here doesn't really matter, it's just an example. So remember, this is the ring of all complex polynomials with two variables x and y. Now we're going to define the following ideal. I is going to be the set of all polynomials p in R, where p has no constant term. So for example, xy would live in there, x would live in there, x squared plus x would live in there, x cubed plus y cubed, x plus, I don't know, x would live in there because all of these polynomials in x and y don't have constant terms. Then you can show that I is an ideal, but it's not principal. The reason why is because I is actually generated by two elements, because if you really think about it, if p has no constant term, then it has to be some linear combination of x and y. So you can write I as follows: I is equal to the ideal generated by x and y. In an ideal generated by two elements, you define this as, well, linear combinations, p of xy times x plus q of xy times y, where p and q are in your original ring R. So when you have no constant term, you can always split your polynomial up into a part with an x factor and a part with a y factor, and this combination isn't necessarily unique. Okay, so now for one of the main things I want to prove in this video. Let's state this as a proposition, maybe it's more like a theorem or something. But anyways, let R be a ring, and let A be some element in R. Then in one of the previous videos, we defined the evaluation homomorphism. It turns out that the kernel of the evaluation homomorphism at A is a principal ideal generated by the polynomial x minus a. Now, if you think about this for the case when r is the real numbers, so you're taking a look at the real polynomials, this pretty much makes sense, because if you have a polynomial where you have a 0 at x equals a, then you have to have a factor x minus a. I think that's called the factor theorem. But it turns out this is also true for any ring. So let's prove this. To show that we have this equality, we're simply just going to show that each of these sets are subsets of each other. And I'm going to start with showing that this principal ideal is a subset of the kernel. And to do so, we're going to let some polynomial p lie inside of this principal ideal. Then what does this mean? It means that p of x is equal to x minus a times q of x for some q in your ring of polynomials. Okay, but we want to show that p is inside of the kernel, so let's just apply the evaluation homomorphism on p. So we have the evaluation homomorphism on p. That's exactly the evaluation homomorphism on x minus a times q of x, but we can split it up because it's a homomorphism. So we have the evaluation on x minus a, then the evaluation on q, but the evaluation on x minus a here, that's exactly equal to 0. So the whole thing is equal to 0 because 0 times anything is 0, and this means that our polynomial p is indeed inside of the kernel of the evaluation homomorphism. And because of that, we've shown that the principal ideal generated by x minus a is a subset of the kernel of the evaluation homomorphism. So that's the first inclusion. Let's show the other inclusions. In particular, we want to show that the kernel of the evaluation homomorphism at A is a subset of the principal ideal generated by x minus a. Now to do so, let's just choose some polynomial p inside of this kernel. Let p be equal to, I'm going to define it as follows, Rn x to the n plus Rn minus 1, x to the n minus 1, all the way down to your constant term, and I'm going to suppose this guy is inside of the kernel of the evaluation. Now I believe this inclusion here is slightly easier to prove than what I'm about to present if you know how to do division with remainder on polynomials, but we haven't discussed that yet. We'll discuss that in a future video after quotient rings. So I'm going to take a slightly more complicated approach using induction. In particular, we're going to use induction on the degree of p, and the degree of p is precisely equal to n. Essentially what we're trying to show is that this polynomial p is also an element of the principal ideal x minus a. And to show that this holds for all polynomials, we can just simply show that it holds for every single possible degree of p. And that's why we're using induction here. We're going to build up the degrees one at a time. Let's define a predicate p of n to be true if a p also lies inside of x minus a for the degree of p is equal to n. So what's the base case of this guy going to be? It's going to be the case when n is equal to 1. And what happens when n is equal to 1? We have a p of x is equal to r1x plus r0. Now by assumption, we're assuming that p lies inside of this kernel. So this means that p of a, which is exactly r1a plus r0, must give you 0. But now we can rearrange things a little bit. In particular for r0, we're going to replace r0 with minus r1a. So r0 is equal to minus r1a. And we can plug that back into our original equation for p. So this implies that p of x is equal to r1x minus r1a, but we can factor this as r1 times x minus a, and as you can see here, we have a factor of x minus a multiplied by some polynomial in the ring, in particular a constant, so therefore this lies inside the principal ideal x minus a. So therefore the base case, which is p of 1, is true. Okay, let's do the induction step now, and what I'm going to assume is that p of n is true for all n less than k. And from here, we want to show that p of k is true. At the moment, our polynomial p of x looks something like rk, x to the k, plus rk minus 1, x to the k minus 1, all the way down to your constants. Now what I'm going to do is I'm going to try to construct a polynomial with smaller degree than k, so I can use this inductive hypothesis somehow. And the way I'm going to do that is I'm going to define the following polynomial, g of x, and that's going to be equal to p of x, but I want to kill off this first term completely, and I'm going to do that in a bit of a clever way. I could just take off, well, rk x to the k, but because I want my g of x to have some kind of x minus a factor, so I can use my inductive hypothesis, I'm going to subtract off rk x minus a raised to the k. So notice we're still going to get some kinds of x to the k term multiplied by r to the k. So when we do the subtraction here, it annihilates this leading term from your original polynomial. So in particular, the degree of this new polynomial g is going to be less than k. Not necessarily k minus 1 because it might eliminate more terms than just the leading term over here. So it's less than k, that's all we know. And let's take a look at the evaluation at g. So the evaluation homomorphism at a of the polynomial g. We can split this up across this difference here because EVA is a homomorphism. So this is EVA of p minus EVA of r to the k x minus a raised to the k. But notice EVA of p is equal to 0 by assumption. We assumed it up above over here, so we let p be inside of this kernel. And also, if you apply the evaluation homomorphism on this second part of the function, that's also going to give you 0 quite clearly because of this x minus a factor. So this guy over here is also going to give you 0. And overall, the evaluation homomorphism applied to g is going to give you 0. So what do we know from this? We know that g is inside of the kernel of the evaluation homomorphism at a. And we also know that the degree of g is less than k. But now notice, by the inductive hypothesis, we know that a p of n is true for any n less than k. And what exactly is the proposition is that if you're in the kernel, then you're also in this principal ideal x minus a. Therefore, by the inductive hypothesis, g must also lie inside of this principal ideal x minus a. So now hopefully you see where everything comes together now. We have this polynomial p. We're going to rewrite this as a g plus this extra term we subtracted. So now we have p of x, that's equal to g of x plus rk x minus a to the k. But remember, g of x, that was inside of this principal ideal, so we can rewrite this guy as, let's say, h of x times x minus a plus rk x minus a raised to the k for some h inside of the ring of polynomials. And now we just simply have to factor out an x minus a everywhere. So this is equal to, we have h of x plus rk x minus a k to the minus 1, and then multiplied by x minus a. And notice that we can have k minus 1 because, well, we kind of assumed that k was greater than 1 because we already took care of the base case here. We're not going to get like a negative exponent here. So therefore, we've shown that this p of x lies inside of the ideal generated by x minus a. And p of x was a degree k polynomial, and since p of k is true, by induction, we know that p of n is true for all n. And because it's true for all n, which was the degree of p to begin with, then every polynomial that was inside of that kernel already is also inside of the principal ideal x minus a. And that completes the proof for this equality of sets. So it's a fairly useful equality to have. We're probably going to use it again in one of the future videos, but that's going to be all for this video on principal ideals. In the next video, we're going to start constructing the quotient ring. So I hope you guys enjoyed this video, and I'll see you guys in the next one.